spiral galaxies. We start with the one you already picture when someone says galaxy. That's not an accident. It's the shape evolution favors when a rotating cloud of gas has enough time and enough spin to settle down. Take the Milky Way, home, a flat disk roughly 100,000 light years across, holding somewhere between 100 and 400 billion stars. The sun sits in one of the spiral arms, about 27,000 light years from the center, orbiting the galactic core once every 230 million years. The last time we completed a full lap, there were no flowers on Earth yet. Not one. Here's the part that should genuinely bother you. Those graceful spiral arms aren't made of the same stars forever. They're density waves, traffic jams of gravity moving through the disk, compressing gas as they pass, lighting up new stars that burn hot and blue and die fast right along the arm before drifting out of formation. The arm is a pattern, not a place. Stars pass through it like cars through a slow section of highway, then speed back up and scatter. Here's the thing that shouldn't be possible: spiral galaxies spin too fast. Measure the orbital speed of stars near the edge of the Milky Way's disk, and by the visible mass alone, they should be flung off into deep space entirely. The galaxy's gravity simply isn't strong enough to hold them in a stable orbit at that speed. It doesn't happen. Something unseen is providing the extra pull, a vast, invisible halo of dark matter, several times more massive than every star, planet, and gas cloud in the galaxy combined, wrapped around the visible disk like a shell around a much smaller yolk. We can't see it, touch it, or detect it directly. We only know it's there because the galaxy is spinning like it has a coat we can't see. At the center of nearly every spiral, there's something waiting, a supermassive black hole. Ours is called Sagittarius A, about 4 million times the mass of the sun, and it has sat there quietly for billions of years, while stars, planets, and eventually us orbited a few thousand light years away without a clue. Let that sink in. You live inside a slow motion pinwheel, spinning around a black hole, and you'll never feel it move. Spirals themselves aren't one uniform club. Astronomers split them into a rough sequence, SA, SB, SE, based on how tightly the arms wind and how large the central bulge is. And SA galaxy has a fat, dominant bulge and arms wound almost as tight as a cinnamon roll. An SE galaxy is nearly the opposite: a small bulge, loose, sprawling arms, gas-rich, and still actively forming stars. The Milky Way sits somewhere in the middle of that sequence. The Andromeda Galaxy, our nearest large spiral neighbor, is a similar type, and roughly 1 trillion stars strong, more than double our own star count, even though the two galaxies look deceptively similar from a distance. But spirals aren't all symmetric swirls. Some of them cheat. Barred spiral galaxies. Same basic plan: disk, arms, central bulge, except a straight bar of stars cuts through the middle like a rigid rod bolted through a pinwheel. And here's the twist: the Milky Way is one of these. We are not the tidy textbook spiral. We're the version with a bar. The bar isn't decoration. It's a gas pump. Its gravity funnels material inward from the outer disk toward the galactic center, feeding star formation and eventually feeding the central black hole itself. Roughly 2/3 of spiral galaxies in the nearby universe have a bar. It's the more common shape, not the exception. We just didn't know it about our own galaxy until the 2000s, when infrared surveys finally saw through the dust blocking our view of our own core. Here's the fact that changes everything. Bars are thought to be a sign of a maturing galaxy, a structure that emerges only after a disk has been stable and undisturbed for billions of years. In other words, the bar is a scar of stability. A galaxy has to survive a very long time, mostly unbothered by mergers or violent collisions, before it can grow one. We live inside a structure that is, in a very real sense, a monument to cosmic peace and quiet, which is unsettling, considering peace and quiet never lasts. NGC 1300, roughly 61 million light years away, is one of the most photographed barred spirals in the sky. A bar so long and so pronounced that its two spiral arms seem to spring directly from its tips, rather than curling out from a central bulge at all. It's a reminder that barred spiral isn't a narrow category. It's a spectrum from a faint gravitational hint of a bar all the way to a structure so dominant it redraws the entire galaxy around it. Because not every galaxy gets to keep its shape. Elliptical galaxies. If spirals are pinwheels, ellipticals are cannonballs. Smooth, featureless blobs of stars with no arms, no disk, barely any new star formation at all. And here's the reframe: these are not young, chaotic galaxies. They're the opposite. They're often the oldest, most finished objects in the universe. Ellipticals range enormously in size. Some are modest, a tenth the mass of the Milky Way. Others are true giants, the largest known galaxies in the universe, sitting at the centers of galaxy clusters, containing trillions of stars packed into a shape like a squashed sphere. IC 1101, one of the biggest ever measured, may span up to 4 million light years, 40 times wider than our entire galaxy. Here's the fact that changes everything. Most giant ellipticals are built from collisions. Two spiral galaxies collide, their gas gets shocked and consumed in one enormous burst of star formation. Their orbits scramble into gravitational chaos. And what's left, after a few billion years of settling, is a smooth, featureless ball with no memory of ever having arms at all. The galaxy doesn't just change shape, it forgets its own history. Which means the most peaceful looking galaxies in the universe are, structurally, crash sites. Wreckage that healed into something serene. Something to think about the next time calm looks like the end result of violence, not the absence of it. Look closer at an elliptical, and you'll notice something a spiral doesn't have nearly as much of: swarms of globular clusters, tight spherical balls of hundreds of thousands of ancient stars orbiting the galaxy's core like a cloud of satellites. A giant elliptical can host tens of thousands of them, far more than the couple hundred that orbit the Milky Way, a leftover census of every smaller galaxy that got folded into the merger that built it. Count the globular clusters, in other words, and you're counting old scars. Not all ellipticals are giants either. Astronomers classify them on a scale from a 0, nearly a perfect sphere, to a 7, stretched into a flattened lens. And at the very top of the size scale sits a special subtype called a CD galaxy, a supergiant elliptical found only at the dead center of massive galaxy clusters, surrounded by a faint, extended halo of stars, stripped from every smaller galaxy that ever wandered too close and got torn apart. A CD galaxy doesn't just win the collision, it wears the losers as a diffuse, glowing outer coat. Between the pinwheel and the cannonball, there's a shape that can't decide which one it wants to be. Lenticular galaxies. Picture a spiral galaxy that used its gas up, or had it stripped away until the spiral arms simply stopped forming and faded out, leaving a flat disk and a central bulge with no visible structure in between. Astronomers classify it as 0, a hinge point between spiral and elliptical. Here's the twist: a lenticular galaxy isn't necessarily old in the way an elliptical is old. It's often a spiral that got interrupted. Strip a spiral of its interstellar gas by ramming it through the hot plasma at the center of a galaxy cluster, for instance, and star formation shuts off within a few 100 million years. No new blue stars to light up spiral arms. No fuel left to feed them. What remains is a disk of aging, reddening stars, ghost-shaped, holding the outline of a spiral with none of the machinery still running. The galaxy NGC 5866 is a textbook example. A razor-thin disk seen edge-on, cut through by a dark lane of dust, with almost no active star formation left inside it. Here's the part that should genuinely bother you. This can happen to any spiral, including possibly ours, given the right encounter with the right environment. Shape is not destiny. It's just where a galaxy happens to be in the process of running out. Lenticulars are strangely common in one particular kind of neighborhood, dense galaxy clusters, where hundreds or thousands of galaxies drift through a shared bath of hot, thin plasma. Every spiral that passes through that plasma gets scoured, its gas physically pushed backward and stripped away by the pressure, in a process astronomers call ram pressure stripping. Live in a crowded part of the universe long enough, in other words, and the crowd itself will eventually starve you. Running out of gas produces one kind of chaos, but some galaxies never had order to lose in the first place. Irregular galaxies. No spiral arms, no smooth ellipse, No symmetry at all, just a chaotic scatter of stars and gas clouds that refuses to resolve into any clean shape. And here's the reframe: this isn't a failure of formation. It's often violence caught mid sentence. The two most famous examples are practically in our backyard: the Large and Small Magellanic Clouds, satellite galaxies of the Milky Way, visible to the naked eye from the southern hemisphere as faint smudges that ancient sailors used for navigation. They're irregular because they're being gravitationally mauled by our galaxy's much larger mass, torn and stretched into streams of gas that trail behind them across 100,000 light years of space, a structure called the Magellanic Stream. Here's the fact that changes everything: many irregular galaxies are actually caught in the act of merging or being disrupted, which makes them some of the most intense star forming environments in the universe. Tidal forces compress gas clouds violently, triggering bursts of starbirth far more efficient than anything happening in a calm, orderly spiral. So, the ugliest, most disorganized galaxies in the sky are, in a sense, the most alive. Chaos, it turns out, makes stars faster than order does. There's a second flavor of irregular galaxy that never had a clean shape to lose in the first place: small, low mass systems that formed clumpy and never gathered enough gravity to smooth themselves into a disk or a sphere. Sextans A, a modest irregular a few million light years away, looks less like a galaxy and more like a loose box of stars someone shook and never bothered to arrange. It's a reminder that order, in galaxies as in most things, takes mass, time, and a fair amount of luck. But irregularity is one thing. Some galaxies are chaotic, not because they're colliding, but because they're barely galaxies at all. Dwarf galaxies. Here's the reframe up front: they are, by a wide margin, the most common type of galaxy in the universe. Not spirals, not ellipticals. Small, faint, unglamorous dwarfs. And there are vastly more of them than every other type combined. A dwarf galaxy can contain as few as a few hundred million stars, sometimes even less, a rounding error compared to the Milky Way's hundreds of billions. Our own galaxy has dozens of confirmed dwarf satellites, with the closest, the Canis Major Dwarf, currently being torn apart and absorbed into the Milky Way's outer halo right now, mid-meal, a slow-motion cannibalism spanning hundreds of millions of years. Here's the fact that changes everything. Dwarf galaxies are thought to be the fundamental building blocks of every large galaxy in the universe. In the early cosmos, small clumps of dark matter and gas collapsed first, forming dwarf-sized structures. And over billions of years, those structures merged again and again, growing into spirals and ellipticals through repeated collision and absorption. The Milky Way itself was built this way, and traces of at least one ancient dwarf galaxy it swallowed, called Gaia Enceladus, still show up in the orbits of stars near the sun today. Let that sink in. Somewhere in your night sky, you are looking at the scattered, digested remains of galaxies that no longer exist as themselves because something bigger ate them and became a little more of what it is because of it. Dwarfs come in their own subvarieties, too. Dwarf spheroidals are faint, gas poor, ancient, small ghost towns of old red stars with nothing left to build with. Dwarf irregulars still hold gas and still form stars in fits and starts. And blue compact dwarfs are caught in the middle of surprising bursts of star formation, despite their tiny size, punching well above their weight in brightness for a galaxy that might contain less than 1% of the Milky Way's mass. Small does not mean simple. It just means easier to overlook. Some of that eating produces quiet absorption, but some of it lights the sky on fire. Starburst galaxies. These aren't defined by shape at all. Spiral, irregular, doesn't matter. They're defined by rate. A starburst galaxy is forming stars at a pace tens to hundreds of times faster than a normal galaxy like the Milky Way, and it's usually the result of a recent violent trigger: a galactic collision, a close gravitational encounter, a sudden inflow of gas. The Cigar Galaxy, MADI 2, is the textbook case: a galaxy 50 times more luminous in infrared light than a typical spiral, its center forming stars roughly 10 times faster per year than the Milky Way manages across its entire disk. That intense star formation drives a superheated galactic wind, blasting gas and newly forged elements out of the galaxy's core at speeds over 1 million miles per hour, visible as a plume extending tens of thousands of light years above and below its disk. Here's the fact that changes everything. A starburst can't last. At the rate these galaxies burn through gas, they'd exhaust their entire fuel supply in as little as 10 million years, a blink, cosmically speaking, compared to the 10 billion year lifespan of a typical galaxy. Starburst galaxies are structurally galaxies burning the candle at both ends. Spectacular, temporary. Doomed to quiet down one way or another once the fuel runs out. The most extreme starbursts of all show up during galaxy mergers still in progress. The antennae galaxies, two spirals roughly 60 million light years away, are caught mid-collision, their outer stars flung into two long, curving tidal tails that give the pair its name, while their cores plow through each other and ignite thousands of new star clusters in the compressed gas between them. It is quite literally a slow-motion collision spanning hundreds of millions of years, and we are watching one single frame of it. Every firework fades. But some galactic centers don't burn out. They just keep feeding something that never gets full. Active galaxies and quasars. Here's the reframe. This isn't really about stars anymore. At the center of an active galaxy, the supermassive black hole isn't dormant like ours. It's actively feeding, pulling in gas and dust that spirals into a blazing accretion disk, heated by friction to millions of degrees, radiating more energy than every star in the host galaxy combined. A quasar is the most extreme version. The word stands for quasi-stellar radio source, because when they were first discovered in the 1960s, they looked like ordinary stars in telescopes, just points of light. Except they weren't stars. They were the blazing cores of galaxies so far away and so bright that their light has been traveling toward us for over 12 billion years, meaning we're seeing some of them as they existed when the universe was less than a tenth of its current age. Here's the number that should genuinely bother you. The brightest quasars can outshine their entire host galaxy, 100 billion stars, by a factor of 1,000, using a black hole's feeding disk alone. The most distant quasar ever confirmed, cataloged in 2021, existed when the universe was barely 670 million years old, roughly 5% of its current age, and yet it already carried a black hole over 1 billion times the mass of the sun. Nobody has fully explained how a black hole that massive could grow so fast so early. It's one of the open puzzles current telescopes are still chasing. And some of them power jets, twin beams of particles blasted out at nearly the speed of light, perpendicular to the accretion disk, stretching for hundreds of thousands of light years, farther than the galaxy that spawned them is wide. Here's the fact that changes everything. Nearly every large galaxy, including the Milky Way, likely went through an active quasar-like phase billions of years ago when it had more gas to feed on and its black hole was hungrier. Our own galactic center is quiet now, essentially starved and dormant, but it wasn't always. And it might not stay that way, because if the Milky Way collides with Andromeda, as it's on course to do in roughly 4.5 billion years, the resulting inflow of fresh gas could wake Sagittarius back up, if only for a while. Let that sink in. The blackness at the center of our galaxy has already had its loud phase. We simply weren't here, and possibly won't be here, to see it. Not every active galaxy screams the same way. Safer galaxies are quasars' quieter cousins, spirals with visibly active, bright centers, but not so overwhelming that they drown out the rest of the galaxy around them. Radio galaxies pour most of their energy out not as light, but as radio waves, often through jets so large they'd stretch well past the orbit of Pluto and keep going, dwarfing the visible galaxy that launched them. And blazars are simply quasars caught with a jet pointed almost directly at Earth, the same phenomenon, viewed down the barrel, appearing to flicker and flare with a violence that has less to do with the object itself and more to do with the unlucky angle we happen to be standing at. So what do all these shapes actually mean? They're not random, they're a record. A spiral is a galaxy with a stable disk and fuel still in the tank. A barred spiral is a spiral old enough to grow a structural scar of long-term stability. An elliptical is a wreck that healed into something smooth. A lenticular is a spiral running on empty. An irregular is a galaxy actively being torn apart or born from a collision. A dwarf is a building block, either primordial or half digested by something larger. A starburst is a galaxy in the middle of an unsustainable growth spurt. And an active galaxy or quasar is a black hole having a very loud meal, one that every large galaxy, including our own, has almost certainly had. Here's the part that should genuinely bother you. None of these are separate species. They're stages. Given enough time, enough gravity, and the right collision at the right moment, a spiral can become a starburst. A starburst can settle into a lenticular. A lenticular can merge into an elliptical, and an elliptical can sit quietly at the center of a cluster, slowly swallowing whichever dwarf galaxies wander too close. The Milky Way itself has already been several of these things in sequence, and will likely be several more before it's done. We happen to be looking at it during the spiral phase, the stable one, the one with flowers and oceans and stick figures asking questions about it. And that phase has an expiration date we can actually calculate. In roughly 4.5 billion years, the Milky Way and Andromeda will begin to merge, two spirals, each holding hundreds of billions of stars, falling into each other under gravity that's been pulling them together for their entire existence. Almost no individual stars will collide. The space between them is too vast for that. But the shapes will not survive. Tidal forces will fling arms into long streamers, the flat disks will thicken and scramble, gas will get shocked into one final burst of star formation, and after a few billion years of settling, what's left of us and them will likely relax into a single smooth elliptical. Astronomers already have a name ready for it: Milkomeda. Every category in this video is really just a snapshot of that same process, running at a different speed at a different stage in a different galaxy. So the next time you look up and see a faint band of light arcing across a dark sky, remember what you're actually looking at, not a fixed, finished object. A moment. One frame in a billion-year film that started with clumps of dwarf galaxies merging in the young universe and won't finish until long after anything alive on this rock is around to watch it. Not bad for stick figures on a rock.